Welcome to lesson 4 entitled Mass Structure. In class, we looked at a Welcome to lesson 4. Welcome to lesson 4 entitled Mass Structure. In class, we looked at a copper sulfate hydrate, and we tried to figure out the number of moles of water. Turned out that there was exactly 5 moles of water per every 1 mole of copper sulfate. Many groups actually figured that out. Here's an example of one that did. I'm showing this one because I really like their model. Clear procedure. Notice they even indicated that they heated it to constant mass. We got a really nice diagram here, clean data table, and clean solution. So easy to read, great example of a good model. In 2007, a problem like this showed up on the AP test. They had a magnesium chloride hydrate, and they asked you to figure out the formula of that. And they gave you some data here. So if you look at it, you got the weight of the empty crucible. They just call it a container here. The weight containing the hydrate, we'll draw that blue. They heated it, and the mass went down because you lost a little bit of water. Okay, but the assumption is that there's a little bit of water left, and it turns out there was because they heated it again, and the mass even went down again. And they heated again to constant mass, and it didn't really go down. I mean, forget about this thousandths place. If you look here, 23.97, 23.97, they pretty much heated it to constant mass. So they ask you some questions. The first was, how can they conclude that all the water was removed? So simply, they did heat it to constant mass. That's a simple way to conclude that all the water was removed. Okay. Then they ask you to calculate the number of moles of water lost. And let's just think about how that would be done. Okay. If you look at this second value, 25.825, okay, if you subtract from that this last value, 23.977, you're going to then get the difference, which is the water. That'll give you the mass of water. You can divide by 18 and get the moles of water. And then they ask you to determine the formula of the hydrate. Well, you can't just get the mass of water to do that. You need to get the mass of the magnesium chloride as well. And if you look at this first value, the container, and you look at this last value, the only difference is that leftover salt there, which is the magnesium chloride. Subtract those, convert it to moles, and you are going to get the moles of magnesium chloride. So what this video is meant to do is give you a system for finding out the formula of a hydrate, or really the formula of any compound when you have the grams of each. Now this is something that everybody did last year, but we're going to be looking at it through more of an experimental lens this year. So if you look at the data here, this is just the AP rubric for this problem. No additional mass was lost during the third heating, indicating that all the water of hydration had been driven off, so heated to constant mass. If you notice here, they're subtracting those two values and then dividing by 18 to get the moles of water. And here, they're subtracting the two values we talked about earlier and dividing it by the molar mass of MgCl2 to get the moles of MgCl2. Now you notice they do something really specific here. They picked the smallest value, and that value is this. And they divided the moles by it. And they ended up with 6. Okay? This process, picking the smallest mole value and dividing both by it, is always going to yield somebody who's 1 and somebody who is something else. And it's a really, really nice procedure for going about doing problems like this. So let's do a few examples after I give you some notes. Okay. So first off, here's another multiple choice problem. Looks like a lot of writing, but really it's getting at this heating to constant mass idea. And I really want you to, I'm going to read this, and I want you to realize that a problem like this that has a lot of text is more often than not really, really easy. So to determine the percentage of water in a hydrated salt, the student heated 1.2346 grams, that's ridiculous. I don't know what scale goes that specific, but whatever, of salt for 30 minutes. When cooled to room temperature, the sample weighed this amount that I'm too lazy to read. After the sample was heated for an additional 10 minutes and again cooled to room temperature, the sample weighed 1.1632, so it lost some more water. Which of the following should the person do next? Without even reading it, you should be guessing. The student should heat it again and see if it stays constant. So use the smallest mass value to calculate the percentage of water. Bleh. Repeat the experiment with a new sample of the same mass and average the results. Dumb. Repeat the experiment with a new sample that has different mass. Why? Reheat the sample until it has constant mass, or until its mass is constant. This idea of heating to constant mass is a very, very important laboratory procedure for you to do whenever you're trying to remove water from a substance. Okay, so let me give you some notes on this process. Okay, so these notes are going to help you find the formula of a compound. I'm not going to call it the empirical formula because I don't want you to think about it in terms of empirical or molecular. Let's just think about it in terms of a formula. Okay, so I'm going to do this in red here. Number one, it's got a little jingle to it. Percent to mass. And what I mean by that is anything that you see, let's say it said 9%, you can just call that 9 grams. You can always just assume that you have a 100-gram sample, so 9% would be 9 grams. So your percent to mass. Now, if you already have mass, you don't have to do this step. So step 1 is often optional. Step 2 is not. Mass to moles. Okay. So whatever you have for your gram value, you're always going to convert it to moles, just like we do with stoichiometry. Very, very, very important first step. Divide by small. Okay. So here, if you have two numbers, let's say 0.20 and then you have 0.40, what you're going to do is you're going to pick the smallest one. Here, that's 0.2. And divide them both by it. And you're going to end up with somebody who is 1, and in this case, you have a 2. Okay. And the last step is also optional, and that is times to whole. And you're not always going to have to do this. But let's say, and let's look at some circumstances. Let's say you end up with 1 for one thing, and you end up with 1.33. So if you end up with these two numbers, you always want the formula to have whole numbers. 1's a whole number, but 1.33 sure isn't. So you'd multiply them both, in this case, by 3. This is going to end up being 3, and this is going to end up being 4. Anything that's 0.33, you'd multiply by 3. Now you have another circumstance where you could have somebody who's 1 and someone who's 1.5. What's the closest whole number? In this case, it's 2. So you'd multiply it by 2, and this would be 2, and you'd multiply this by 2, and this would be 3. So there's only 2 circumstances where I'm ever going to make you multiply to whole. One case when you'd end up with 1.33. In that case, you'd multiply by 3. And in the other case, where you'd end up with 1.55, and in that case, you'd multiply by 2. So percent to mass, mass to moles, divide by small, times to whole. Percent to mass, mass to moles, divide by small, times to whole. Percent to mass, mass to mole, divide by small, times to whole. Percent to mass, mass to mole, divide by small, times to whole. Percent, all right, I'll stop. You get the deal. Optional, this step, and the fourth step. So let's do some examples. So this first one. You got somebody who is 30% sulfur and 70% fluorine. What is the formula? They say empirical formula, who cares? So percent to mass. 30%, I can just call it 30 grams S, and I can call this 70 grams F. Mass to moles. 32 grams per every 1 mole of S. So that's going to yield 0.9375 moles. And 19 grams per every 1 mole of fluorine. And that's going to yield 3.684 moles. And usually with a problem like this, I don't round until the very end. Okay. Divide by small. So I'm going to divide this by 0.9375, and that's going to be 1. And I'm going to divide this by 0.9375, and that's going to be 4. So my formula is S1, or 4, and the answer is C. And then I could go on and draw the Lewis structure for this if I wanted to, and we're going to be doing that in class. Wink, wink. Next one. Percent to mass to moles divided by small times to whole. All right, well, they already gave me grams, so I don't have to do percent to mass. 3.21 grams of sulfur, 11.4 grams of fluorine. I know that there's 1 mole, there's 32 grams. This is going to be 0.10 moles of S, and 1 mole, there's 19 grams here. So that is going to be 0.6 moles F divided by small, 0.1, that's 1, 0.10, that's 6, S1, F6, and I could do the Lewis structure for that. You can probably tell I'd have to expand the octet, and in this case, S is in at least n equals 3. It's got that empty d orbital, and I could go ahead and do that. Now, I'm sure you could look at this and be like, okay, it's 1 and 6, and I encourage you to do that if you want to. Definitely don't have to do this process here. Let's do another one. Percent to mass to moles. Oh my gosh, they actually already even gave me moles. What? That's hella easy. Can't believe that. Typical move on multiple choice, by the way, is to do this. So divide by the small, 0.55 moles equals 1 mole Te, 0.55 moles equals 2 moles of K, and 0.55 moles equals 3 moles. So I have K2, Te1, O3, and that's going to give me C as my answer. All right, last one here. When hafnium is heated, blah, 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 it's found to contain 62% HF. So 62% percent to mass, 37.4% percent to mass, Cl. Mass to moles don't really deal with hafnium that much. So let me look on my periodic table. For every 1 mole of hafnium, it's 178 grams. So that's going to give me 0.349 moles of hafnium. I think that's how you say it. And the molar mass, 35.4 grams per every 1 mole of Cl. That's going to give me 1.05 moles divided by small, so 0.349. That's 1. 0.349. That's going to give me 3. I think this is 1 point. Not sure what this number is. 1.85, 1.05. Either way, you guys can do that out. You get 3 here. Answer is HFCl3. Okay, so for your multiple choice problem, what is the empirical formula of a hydrocarbon? Okay, so this means something that contains just carbon and just hydrogen. That is 10% hydrogen by mass. So the other percentage, the other 90%, is obviously carbon. Okay, go ahead and do that. And hint before you do this, this is going to be one where you're going to have to times the whole. If you get 1.33, you'll multiply both by 3. If you get 1.5, you'll multiply both by 2. Thanks a lot.